Well, hello students. You might not know it, but this is the lecture, this is the talk you've been waiting for. If nothing else, you've been waiting all weekend, even though you didn't know you were waiting for it. We're going to introduce some rules for differentiation, and if this weren't being recorded, I think I would hear claps and hoorays. You don't believe me, do you? Well, let's see. If you've been working those derivatives using the limit definition, here goes. This looks like a pretty good laundry list, but trust me, this is going to help you a whole lot. And most of this is pretty simple, really. Start off with something very simple, the constant rule. And we're talking about derivatives, remember. We're taking derivatives of constants. Well, if you've got a constant, that means like y equals 7. Well, no matter what x is, y equals 7. It's constant. There you go. So, first of all, let me sneak in here with my pen. Here we go. Set up the pen so I can make marks. And here's our constant. Now, for your notes, maybe you want to put in your favorite number there. If you're a science fiction fan, you might want to put 42. So you're taking the derivative of 42. In other words, you might say, okay, what are we actually starting with? We're actually starting with y equals 42. And what's the derivative of that? The derivative of any constant is 0, regardless of what it is. If you have y equals pi, pi is a constant. The derivative is 0. If your favorite number is 86, y equals 86 is your function. The derivative, 0. The derivative of every constant function is 0. Some quick examples to drive this in, because this is important. Y equals 7. If that's your original function, derivative, 0. F of x equals 0, which means y equals 0. Derivative, 0. Y equals 2, 0. G of t equals negative 3 over 2. That's a constant, 0. Just some different looks from the functions and the derivatives that are derived from those original functions. That's why it's called a derivative. Okay? Now, you think I'm getting something more difficult? Well, only by a hair. The power rule. And you could say, where's my marker? Here we go. Compared to what you had to do for section 2.1, where you're finding derivatives using the limit definition, this gives you great power. This saves you so much time. You have some nice polynomials that have just even powers, looks real nice. It's continuous and all that good stuff. Well, now, instead of spending, frankly, 15 minutes, half an hour for a long polynomial, maybe even an hour to do it, to get the derivative. Now you'll be able to do it in maybe a minute or less. That's something to celebrate. Now, Where do these rules come from? They come from the fact that as you expand x plus delta x, or in our case, there we go, first one will be x plus h squared, which will be x squared plus 2xh plus h squared, and so on. The x plus h, or the delta x squared is a factor of most of those terms. So when you're taking the derivative, a lot of those things go away because delta x alias h becomes so close to 0, even the factors, no matter how big they are, when you make delta x or h small enough, they, for all practical purposes, disappear. And that makes using the power rule fantastic. Here's the power rule. It says the derivative of, and you could think of this as starting off with y equals some number, pick whatever number you want, some number in front, getting carried away, getting so excited. There's our original function, and the derivative of that, if we want to, we can call that dy dx, and the derivative, oh, I've still got those marks, oh well. The point of the power rule is you take this power, the n, and bring it out front. So the derivative will be n goes in front, and the power of x gets reduced by 1, n minus 1. It's that easy. So if we take an example, let's suppose I just say x to the 5th power. What's y prime? Bring the 5 out front and reduce the power of x by 1. And there's your derivative. Bring the exponent out front as a factor and reduce the exponent by 1. Now, just to remember that this means if you have, where's my cursor? There we go. If we have something very simple like this, remember in our head we're thinking that's x to the 1. So what's the derivative? The derivative is 1 comes out front, and we reduce the exponent by 1. Translated, what does that mean? Our derivative is 1 times an x to 0 power is a 1. So we have 1 times 1. The derivative of x is 1. That's a good one to remember. You don't even need to go through this process if you just remember, if you're taking the derivative of just x, it's just a 1. A shortcut that if you memorize it, that just makes things a bit faster. Because you don't have to bother bringing the 1 out front. You know the derivative of x is 1. And that's consistent with the fact that the slope of the line, y equals x, here's our line, there's our equation, there's the line that goes along with it, and the slope is 1. Because for every x moving by 1, the y moves by 1. Delta y over delta x, 1 over 1, slope is 1. Now here's something really big in differentiating. The big word here is rewriting. The power rule, if you'd had a chance to relax and enjoy it, you realize it's so powerful and so easy. And anytime you can rewrite a function so it looks like it uses the power rule, you're home free. Just bring that exponent in front as a factor, reduce the exponent by 1, bingo, you've got the derivative. So, since this function right here does not look like our power rule thing, but if you rewrite this as x to the negative 2, differentiating is a piece of cake. Just bring that negative 2 out front, so you'd have negative 2x, and the exponent, remember, reduce it by 1 or subtract 1 from it, so it'd be, if you want the derivative of that, dy dx. There's our negative 2 in the front, and our negative 3, which is 1 less than the negative 2. Pretty good, huh? So you take the original function, rewrite it, differentiate. Then, when you got in the form of the power rule, and you're done with a little bit of simplification. Remember that when you did the rewriting, sometimes you might need to rewrite this at the end and put it in regular format. So instead of x to the negative 3, which is sort of not the way you want to write it, because this is the normal way of writing that derivative, not with a negative exponent. Simple. So when you rewrite, you might have to rewrite again to put it back in normal fashion. So, find the slopes of a graph of f of x equals x squared. Remember, x squared is a parabola. This isn't a line. The slope is different all different places, depending on what the x is. So, first thing you do is you write the function. So if you've gotten this from a book, for example, and you know how that goes, or whatever it is, even if it's on the screen, make sure you got the function written right. First of all, you want the derivative because that's going to be your slope everywhere. Bring the 2 out front. Our x has an exponent that's 1 less, so it'll be x to the 1, also known as 2x. Now what does this mean? This means that the slope can be calculated by 2x. Now since it isn't 2 everywhere, we have to ask ourselves, where do we want the slope for? Well, part A, let's say, we're talking about an x of negative 2. So somewhere on our graph, we have an x value of 2. What's the slope at that point? Now if we want to, we can actually figure out what the point is. Just put the 2 in for x. This tells us how to find the y. That means the y value is 4. What's the slope at that point? Well, just put it into our derivative. 2 times x, the x is 2. So our slope is going to be 2 times 2. So at this point, our slope will be 4. Pretty steep. So x equals negative 2, slope is a 4. We're not satisfied with that. What about where x equals 1? What's the slope? put the -1 in here. 2 times -1 is -2. Our slope for x equals 1 is a -2. Oops, sorry. Should be a -4 there. Part C. How about for x equals 0? Put the 0 in for the 2x. Slope is 0. How about x equals 1? Just put 1 in for x in the 2x. Slope is 2. And just one more time, where x equals 2, slope equals 2 times x, 4. It's as easy as that. It puts some concepts together, but it all works. So find the derivative, and just put the x values in. Slopes, -4, -2, 0, 2, 4. That easy. There's our parabola, and there are a couple of the points, or actually all the points. They have 2 of the lines drawn in, but all the slopes are put there next to the points. And you can see by looking at the slope of the tangent line how steep some of those would be. And steepness means slope. For example, over here at the first point, this one, if we try to draw a tangent line, you can see right away that's pretty steep. And it's going down, so it's got a negative slope, and so the -4 makes sense. Down here at this next one, the slope is negative again. Not quite as steep. Slope is -2. It makes sense. Down here at the bottom, slope is 0. That makes sense because it's going to be a horizontal line, and so on. Now, the constant multiple rule. This looks like we've got a bunch of rules. It's not really that complicated, so just relax. The constant multiple rule just means that if you have a number in front of your x, that you're going to incorporate that with what you've already got. So, for example, let's throw in a quick example here. Let's suppose your original function is 5x to the third. What's the slope? The slope is represented by the derivative. Now, this is not a straight line, so it's going to be different at different places. So calculus helps us, and today's power rule is fantastic. So what's the derivative? Bring the 3 out front as a factor. So we have 3 times 5 is 15 out front. Remember, that's the 3 times the 5 that was already there. And our x has what for an exponent? 1 less than it used to. And there's our derivative. That's all it means. So if you followed what I said before about bringing the exponent out front as a factor, just because we have a coefficient there, doesn't make it more complicated. Next, this is a representation of what we just did. Bring that n out front, multiply the c times the n, and don't forget to reduce the exponent of x by 1. No matter what it is, subtract 1 from it. Now, it doesn't always have to be an integer, so be careful there. Next, you can put those together, and don't forget to remember how math uses parentheses, the old order of operations trick. So here are 4 examples. So let's see. Well, the first one a day ago with using the limit definition, you might want to throw up your hands and say, I can't do this, although you actually could. It would take a while. Well, in this case, we have a few steps. First of all, it isn't in the form for the power rule yet. Notice the constants. So we'll bring the constant part out first. 5/2. Now the x to the third is in the denominator, so since it's in the denominator, we need to write it as x to the minus 3. Now it's ready. Bring that 3 out front. So when we take the derivative, called y prime this time, negative 3 times the 5/2 will be negative 15 halves. And then x. This exponent right here gets reduced by 1. That means we subtract 1 from it. So it becomes negative 4. Last of all, we're going to put it back together the way it normally would look. So our derivative equals, now I've got the negative 15 over 2, and the x to the fourth means that x needs to go in the denominator with a positive exponent. And there's your answer. Next one. Sneaky. This is a good example because it looks like the first one at first glance. First thing we need to do is rewrite it. I might take this in 2 steps. First of all, get the 5 on the top, that's fine. On the bottom, we actually have to cube the 2x. That means 2x times 2x times 2x, or better yet, 2 cubed times x cubed. 2 cubed is 8, and we've got x cubed. Rewrite this so it's ready to go. We've got 5/8 x to negative 3. Notice the difference on the top. It's different because of these parentheses. Now we're ready to go. We've got a coefficient out front, that's fine. We've got x to some power, we're ready to go. So if I want dy dx, I'll bring that negative 3 out front as a multiplier. We have negative 15 over 8, and we've got x. Subtract 1 from the negative 3, becomes negative 4. It's almost ready, but it's not ready for writing as your final answer. Dy dx. That x to the negative 4 means the x to the fourth should be in the denominator. So negative 15 over 8, and the x goes in the denominator. Done. And there's your derivative. Next one. Maybe you can do this faster than I can. First of all, rewrite. Now note right off the bat, this has a little bit of a different wrinkle. That's why we've got several examples. First of all, there's our coefficient. Notice we've got x to the negative 2, but it's in the denominator. When we bring this up to the numerator so that we can use it with the power rule, we change the sign of the exponent. Well, the same works here. Instead of a negative 2, it'd be a positive 2, or just a 2. And it's ready to go. So differentiate dy dx equals, I'll bring that 2 out front, multiply the 2 times the 7 thirds, the 14 thirds, x, reduce the 2 by 1 there, and we don't need the 1 there. It makes us look like rookies. And put the x on the top or just x out to the right. Either way is fine. And number 4. Okay, this is going to be a little bit more interesting. Let's see how we do with the parentheses. Step number 1, y equals. Rewrite this. 7 goes on the top. That's pretty simple. Notice that what we've got is 3x to the negative 2. The easiest way would be to say negative 2. That means I should have 3x on the top with a positive 2. There's nothing left in the denominator. In other words, it's 1. It's not quite ready to go, though, because there's our 7, but we need to square the 3x, which is 9x squared. So our rewrite is 63x squared. Lost my parentheses up there. Now it's ready to differentiate. Bring the 2 out front, our derivative, and let's use f prime this time just for fun. Bring the 2 out front, we've got 126x. Reduce that square by 1, and we've got 1. And f prime of x equals 126x. There you've got 4 derivatives in no time at all. Imagine trying to do those going through the limit definition. Well, let's not think about it anymore. But remember, when it comes test time, you're going to have 1 or 2 of those where you go back to the limit definition. So don't lose those skills, even though you've got incredible power at this point. Excuse the pun. There's our answers. Should be the same, hopefully. Okay, so sometimes things do get a little bit more interesting. For example, over here, our function is a root instead of just a straight power. So rewrite that as x to the 1/3. Then it's ready for the power rule. Bingo. Just might as well finish this up while we're at it. So what's y prime? Bring that 1/3 out front. X. Now, what's the exponent of the x? Very simple. Subtract 1 from that 1/3. Subtract 1 from 1/3. You get negative 2/3. Oh, negative exponent. Trying to make it more interesting. So here's the 3 that was there before. 1 goes on top. And x to 2/3 goes there. If you want to be a perfectionist, that 2/3 means power of 2 and the root of 3. So we have 3, that's our constant. We've got the cube root of x squared. There you go. You could do other things with it. That's good enough for right now. The next one, there we go. Remember, this is the root that goes in the denominator of the exponent. This is the power that goes in the numerator of the exponent. So So our rewrite looks like this. If I want to differentiate that real quick, bring that negative 4/3 out front. What's the new exponent? Subtract 1 from that. Subtracting 1 from that means subtracting 3/3. So negative 7/3. And you can rewrite it in the proper fashion. So here's an example. You take the square root of x, rewrite it, differentiate, and then simplify. Because if you're writing a good answer, you don't want to use the negative. You want to bring that down to the denominator, and you also want to change that 1/2 to what it represents without using a fractional exponent. Next one. Remember that the 1 and the 2 are just a constant, so bring those out front, leave them alone temporarily. The third root of x squared can be written as x to the negative 2/3, 2 because you're squaring, 3 because the root, and minus because it's in the denominator. And this sets it up to use the power rule. Bring the negative 2/3 out front. Reduce the exponent of x by 1. So you have negative 2/3 and minus 3/3. Minus 3/3 is negative 1. And then a little bit of cleanup. You can reduce because those become 1s. End up with negative 1/3. And because it says a negative exponent, put it in the denominator. And you're on your way. Next one. Split these up. So what it doesn't exactly show you here, but you can take it in one step eventually, is the first thing is you split this up into the square root of 2, square root of x. Then you can write it like this. Square root of 2 just stays that way. You don't have to do anything with it. Change the exponent, or change it from square root of x to x to the 1/2. It's ready to differentiate. Bring that 1/2 out front. Reduce that exponent by 1. 1/2 minus 1 is minus 1/2. These two can be combined just a little bit. And there's your final answer. Sum and difference rules. I know we've gone over a lot, so you might want to pause here and go get a drink or a snack. Come back. Sum and difference rules, though, are pretty easy. In fact, if I didn't show you the sum and difference rules, you'd probably do it by accident. And you'd be correct. So if you want to differentiate y equals 3x plus 2x cubed, you differentiate them separately and put them together. So the y equals 3x. The derivative is 3. Y equals 2x cubed. Y prime equals 6x squared. And just put those two together. And there's your answer. Very simple. Just do each one separately, and whatever the sign is between them, you just keep that sign. This becomes the 3. This becomes the 6x squared, and you got your y prime. That's it. Whether you're adding or subtracting, it works the same way. Just do the individual terms, differentiate each term individually, and keep them together. If you got 3 of them, take the derivative separately. Here's an example. It says, find an equation of the tangent line to the graph of g of x at a certain point. Okay, this puts several things together. First of all, you want g prime of x, because if you're going to get the tangent line, you need to find out the slope. If you're going to find out the slope, you need the derivative of the function. So we'll bring this 4 out front. 4 times 1/2 is 2, so you have negative 2. The x becomes x to the 4 minus 1 is 3. Next one, we've got a plus there. We'll bring the plus out there. 3 out front gives a 9. X cubed becomes x squared. And last of all, remember the derivative of x is 1. So this is just negative 2 times 1 is negative 2. And we're looking for what is going on at negative 1, negative 3 halves. So this gives us the slope anywhere. But we're interested in what is the slope where x equals 1. So just take g prime, and the x we're interested in is negative 1. So we'll take our derivative, and where we have the x, we'll put in negative 1s. 9, negative 1 squared, negative 2. Okay, let's see. So what's the slope at negative 1? Negative 1 cubed is negative 1 times negative 2 is a positive 2. Negative 1 squared is 1 times 9 is 9 and minus 2. So the slope at negative 1, the 2's give us 0, the slope is 9. Not quite finished though, we want the equation of the tangent line there. We've got the slope of the tangent line. And we've got the point. Excuse me. So, remember this formula I said, this is worth memorizing, the point-slope form. Here we go again. Y, now the y sub 1 is negative 3 halves, so there'll be y plus 3 halves equals, the slope is 9, x plus 1, because it's x minus a negative 1. There's our equation. Not quite ready for prime time though. Y plus 3 halves. Oops, what did I do? Equals 9x plus 9. Subtract 1.5 from both sides. Still the 9x. Subtract 1.5 from that. We'll still have 7.5. This line will be tangent to this curve at that point. Now this is where it's really fun to have a graphing calculator. Go up to that y equals key and type in the g of x. I'm not going to write it out. and then type in for y2, type in the 9x plus 7.5, and bingo, you're going to see the first one have a tangent with that with that line. It's really neat to see. After all that work, not a whole lot of work, it's nice to see your work come together, and you can see that the line that you just created is tangent to the original equation. Now, the original equation is a little bit complicated. It gives you a nice curve. That's what polynomials do. But you'll see that line that you created tangent to it. Real nice fun. And that's what we did. There's our slope. There's our curve. And notice there's our tangent line. Now notice the tangent line does intersect the curve at other places. That's irrelevant. All we care is that at this point down here, where am I? At this, here we go. At this point down here, this line is tangent to it. And there's our line. And of course, it's always good to wrap this up with a little bit of an application, since we're talking business calculus. See what we've got here. You want to find the rate of change of a company's revenue with respect to time. So remember, the revenue, where's my cursor? Okay. Remember, revenue is the money coming into your company. And what we're interested in is how fast is that increasing or decreasing. Let's hope that this is a positive number, because we want our revenue to be increasing. Otherwise, we might be out of business soon. So keep this in mind. Many of these problems tell a story. Don't miss the story. Make it a personal thing. Think of it as your business, what's really happening. The revenue is the money coming into the cash register or into your pockets, whatever way you want to think about it. The rate of change of that is how fast is it coming in, or how fast is it not coming in anymore. So here's what we've got. Buffalo Wild Wings. Are you a fan? Will you, after this lesson, go out and get some Buffalo Wild Wings? I probably won't, because it's Sunday and it's closed, but actually it's Monday, sorry. Okay, so we've got the revenue. So we've got an equation here. So the first thing you do would be you might write that as a function of x. Make sure you write the equation on your paper correctly. I know that sounds trivial, but if you don't, you're going to have some trouble. There's our equation for revenue, or function for revenue. Notice t is between 8 and 13 inclusive. That means we're talking about the years 2008 through 2013. That means this model is good for those years. It also means, if you remember your statistics, that if you use this to model something for 2014 or 2015 or something previous, it's a little bit more iffy. This model is for the years 2008 to 2013. but we're in good shape. We're looking for what the revenue is in 2011. How is it changing? At what rate was the revenue changing? Rate immediately should say to you, I think we're back in calculus class again. So the first thing you want to do is find the derivative of the revenue, r prime if you like. So bring that 2 out front, multiply it times the 22.766. The t one will be easy because the derivative of the t itself is 1. So this will be minus 309.59. And the derivative of this part, 0. Remember right at the first of the lesson? So what do we have? There's our derivative at the top. I didn't do that because I didn't want to do the multiplication in real time like this. Where is my cursor? Up here. Okay. So there's my derivative. Notice the 0 out front. This was the 309.59t, and this is the one that had the t squared on it originally. It's only good for years 2008 to 13. So here's our derivative. If we want it for 2011, that means the t, because of our convention, will be 11. We just put the 11 in where the t is. Here's the 11. A little bit of work from the calculator, and 191.13. So what does that mean? 191.13. It means that since it's in millions of dollars, at the end of 2011, the revenue is increasing by $191.3 million per year. That's not a revenue of $191.3 million. It's increasing by that in 2011. And that's it, folks. Let's wrap a bow on this. Better yet, you should be thrilled you don't have to use the limit definition of the derivative for a while. And I'll see you in 2.3. Bye-bye.